So welcome to the video for the cosecant parent graph. And if you recall, sine of x and cosecant of x are reciprocal functions. So the sine of pi over 4 being square root of 2 over 2, we'll take the reciprocal to find the cosecant of pi over 4. So the reciprocal means to flip that fraction. So instead of square root of 2 over 2, we have 2 over square root of 2. We're going to rationalize the denominator by multiplying the top and bottom by square root of 2. And then we'll have 2 square root of 2 over 2, which simplifies to just the square root of 2. So the cosecant of pi over 4 equals square root of 2. And we're going to get a decimal approximation by entering that into the calculator and rounding to 1 decimal place. So square root of 2 is approximately 1.4, which makes sense since half of the square root of 2 was 0.7. Okay, then the reciprocal of 1 is 1. So cosecant of pi over 2 is 1. Then at 3 pi over 4, we have another square root of 2, which is approximately 1.4. The reciprocal of 0 is undefined because if we're taking 0 over 1 and getting its reciprocal, that would be divide by 0, which is an error. So that's undefined. And remember, undefined has the symbol of a circle with a cross through the center. That means undefined. Okay, at 5 pi over 4 in the third quadrant, the cosecant is negative. So this will be negative square root of 2, or approximately negative 1.4. And then at 3 pi over 2, the reciprocal of negative 1 is negative 1. 7 pi over 4, that is the fourth quadrant. So we have another negative square root of 2 since sine is negative in quadrant 4, and that's approximately negative 1.4. Then at 2 pi, we're back at 0 for the sine, and again the reciprocal of 0 is undefined, so that's a circle with a slash through it. So this question here asks what happens on the graph at values where the cosecant is undefined. So at 2 pi and at pi. And since it's a cyclic function, it's going to repeat that pattern. So 3 pi, 4 pi, 5 pi are all going to have an undefined cosecant. And places where the graph is undefined, those are represented by asymptotes. So we're going to find vertical asymptotes on the graph at intervals of pi plus or minus k pi. So let's see what that looks like on the graph. So at pi over 4, we have a point at the square root of 2, which is 1.4. So right under 1.5. Then at pi over 2, we have a point at 1. At 3 pi over 4, we're headed back up now to square root of 2 again. And then at pi, the function is undefined. So we're going to have a vertical asymptote represented by a dashed line at pi. And while we're here, we may as well put in our other vertical asymptotes because there's going to be one every pi units on this graph. So at pi and at 2 pi, those are represented in the table. Then here at 0, we're going to have a vertical asymptote at negative pi and at negative 2 pi. These will all be vertical asymptotes. Okay, then back to our table of ordered pairs. So at 5 pi over 4, now we're in quadrant 3 where cosecant is negative square root of 2. Then at 3 pi over 2, we have a point at -1. And then 7 pi over 4, back down again to -√2. And if you sketch in these curves, they're going to come along that vertical asymptote, bend through these guide points, and then back up along that vertical asymptote. And so they make these alternating upward and downward facing U shapes, similar to a parabola, but not parabolas because of the vertical asymptotes that are fencing them in. Remember, a quadratic function is unbounded across its domain from -infinity to +infinity. This is trapped between these vertical asymptotes, 0 and pi, pi and 2 pi. Now we can repeat this cyclic pattern by making our relative extrema, and then we'll put in our -√2 guide points and our +√2 guide points. And that will be the parent graph showing 2 cycles of cosecant. So the description of this shape, these are alternating U shapes. And there are no zeros. As you can see, the graph never crosses or touches the x-axis, so no real zeros. There's also no y-intercept because the y-axis is an asymptote. We have a relative maximum of -1 and a relative minimum of +1. Okay, the period is the length of one cycle, and in one cycle there's an upward facing U and a downward facing U. So the length of one complete period is 2 pi radians. And our asymptotes are occurring at x equals, and the first asymptote is here at 0, so we'll start with the plus or minus pi, that's our interval between the asymptotes, times some integer k. So we're going to specify that k is an element of the integers, so we know that we have to go full increments of pi to reach the next asymptote. The asymptotes are going to be restrictions on the domain. The domain is not fully unbounded the way sine and cosine's domains are because of these asymptotes here chopping up the graph. So our domain is all real numbers except x's that are not allowed to be, they're not equal to, positive or negative pi times k, again where k is an element of the integers. And then the range is starting at -infinity, and then we go up to this relative maximum of -1, and that's inclusive, so -1 gets a bracket. Then we'll pick up on the other side of this gap at +1, which is also inclusive, and then we head up to +infinity. So constructing the cosecant function, we're going to go through this simulator. So starting in quadrant 1, you can see as the angle gets closer and closer to 45, the function is decreasing, right? Then as we approach pi over 2, right, that's where we hit our relative minimum, and then in quadrant, oops, I lost it, then in quadrant 2, we come back up and head toward that vertical asymptote at pi. Now in quadrant 3, we're coming up from the bottom, right? Notice how the direction changed between quadrants 2 and quadrant 3. And now we're going to approach our relative maximum here at 3 pi over 2, and then we're going to keep going until we get to that vertical asymptote at 2 pi. And that's one cycle of the cosecant function.